CMB Cold Spot begins with a measured irregularity in the universe's oldest light, not with a settled answer. To understand CMB Cold Spot, start with the cosmic microwave background, the cooled afterglow of the early universe. Subscribe for more deep documentary investigations like this. It is not a decorative image of space, it is a measurement of temperature differences across the whole observable sky. Most of those differences are tiny, but they are the seeds from which galaxies and clusters eventually grew. That is why one unusually cold region matters. It asks whether the map is revealing structure, chance, or new physics. The responsible question is not whether the anomaly sounds extraordinary, but whether the evidence can survive ordinary explanations. A serious science film has to hold that tension without turning a question mark into a headline. The cold spot is compelling precisely because it sits between measurement, interpretation, and imagination. The first question is whether the signal is real enough to survive better maps, cleaner statistics, and independent checks. The void explanation begins with known physics and with the distribution of matter between us and the CMB. If a very large region contains fewer galaxies than average, photons crossing it can lose or gain a small amount of energy. That process is connected to the integrated Sachs-Wolfe effect, where evolving gravitational fields leave a weak imprint on ancient light. The difficulty is scale. The proposed void must be large enough, deep enough, and aligned enough to explain the temperature drop. A shallow underdensity can support the story, but it cannot automatically solve the entire cold spot problem. So the Eridanus supervoid is not a magic answer. It is a hypothesis that must be measured against the size of the anomaly. This is where galaxy surveys become essential, because they show whether the foreground universe contains enough missing matter. The stronger the void claim becomes, the more precisely it has to account for both position and temperature. That is why the argument is not simply about finding emptiness. It is about whether the emptiness has the right shape and depth. The evidence matters because every proposed explanation changes the size of the mystery, from ordinary structure to speculative new physics. The collision hypothesis moves into more speculative territory, where cosmology touches brain world and bubble universe ideas. In that framing, another region of space-time could have interacted with our early universe and left a circular thermal scar. The appeal is obvious. The cold spot would become more than an anomaly. It would become a clue about a larger reality. Share your view below. Which explanation for CMB Cold Spot do you find most convincing? But appeal is not evidence, and a multiverse claim must clear a much higher bar than a foreground structure claim. A collision model has to predict a signature, not merely explain one feature after it has already been noticed. The thermal pattern, angular scale, and statistical context all have to point in the same direction before the claim becomes persuasive. For now, the collision idea remains useful as a test of theory, not as confirmation that another universe touched ours. That distinction matters because speculative physics can be scientifically valuable before it becomes scientifically convincing. What keeps the story alive is the discipline of testing an anomaly without turning uncertainty into certainty too quickly. The evidence matters because every proposed explanation changes the size of the mystery, from ordinary structure to speculative new physics. The skeptical explanation is less cinematic, but it may be the most important discipline in the entire investigation. A random field will always contain unusually hot and unusually cold regions if enough of the sky is examined. That means the cold spot must be judged not only by how strange it looks, but by how unlikely it is under standard assumptions. Inflationary physics already predicts primordial fluctuations, and some of those fluctuations will stretch across large angular scales. The danger is retrospective certainty. Once an anomaly is noticed, it can become tempting to build a story around it. Good analysis asks whether the feature was predicted in advance, reproduced independently, and tested against alternate statistics. That restraint does not weaken the mystery, it protects the mystery from becoming a premature conclusion. In science, a surprising pattern is the beginning of an investigation, not the end of one. CMB Cold Spot remains powerful because it shows how science can protect wonder and skepticism at the same time. The honest synthesis is that each explanation carries a different burden of proof. A foreground void is conservative, but it must be physically sufficient. A statistical fluctuation is modest, but it must explain why this region looks so visually striking. A multiverse collision is profound, but it must produce evidence that simpler models cannot absorb. Future surveys can tighten the foreground map, sharpen the void measurement, and test whether the anomaly survives better data. Until then, CMB Cold Spot remains a scientific pressure point rather than a solved case. Its value is not that it proves the wildest idea, but that it forces every explanation to become more precise. That is the proper ending for a cosmology mystery, not certainty, but a cleaner map of what certainty would require.
Subscribe for more, like the video, and tell us which explanation you find most convincing.